In this presentation, we will discuss cleaning and testing methods used in metallic filtration applications. At Carolina Filters, we have personnel who oversee various aspects of the business, including the compliance staff who manages our safety, quality, and environmental programs. Our team of engineers and chemists will design and develop processes for projects. The customer support staff provides communication, information, and technical assistance as needed by our clients. Carolina Filters' commitment to quality is reflected in our ISO program. Being ISO certified for more than 20 years, we recently completed our 2001-2015 certification. At Carolina Filters, we use a computerized process tracking program, which allows us to track and document filters and parts as they go through our process. At Carolina Filters, we are committed to and invest in new and cutting-edge technologies as we work toward process improvements and expanded services for our clients. So what do we do? Carolina Filters specializes in developing technical cleaning and testing processes for filters and associated parts. For refineries, we develop processes that provide filtration solutions for various refining applications, such as FCC slurry oil, catalyst recovery, and blowback or backwash systems. A major part of cleaning involves what we call a deep cleaning solution that is needed when refiners encounter filtration upsets due to variations in feedstock, additive mix, and embedded particulate that plug the media and results in short filter life. Possible contaminants that typically result in performance issues are materials such as asphaltenes, salts, and inerts embedded within the media matrix. When the particle size distribution within the feedstock is outside of the normal range for the refinery, filtration issues can occur. Also, if there are issues within the unit, filters can be negatively impacted either from contamination or possible damage from the process upset. Here are typical pictures of filters processed at Carolina Filters. One picture shows a filter that has been in service for about 5 years. You can see the discoloration and contaminant on the bundle. The other pictures show filters that have either been cleaned or that are new. Along with filters, we clean auxiliary equipment, from heat exchangers and pumps to mixers and tube bundles. Whether the part can be cleaned will depend on size, configuration, metallurgy, and contaminant. So how do we clean? At Carolina Filters, the approach to cleaning filters starts with gross contaminant removal, which is the removal of loose solids, oils, or materials packing the internals of the filters. After gross contaminant removal, deep cleaning methods are used to remove embedded contaminants as seen in the cross-sectional views of the porous metal media. The embedded contaminants can result in short filter life, high initial delta P, and quality issues. Depending on the chemistry of the contaminant and the size, metallurgy, and configuration of the filter, the deep cleaning process may involve one or more of the following. For organic contaminants such as asphaltenes, high-temperature oxidation processes may be used. Ovens, convection or vacuum, and molten salt baths are examples of high-temperature oxidation process equipment. However, if there are inorganics, salts, and other contaminants that can be solubilized with targeted chemistry, then solvents or aqueous chemistries may be used. Even with high temperature and chemical processing, there is generally a need for physical or mechanical cleaning steps. Ultrasonics can provide excellent surface cleaning results in the removal of hard particles loosely held or trapped within the outermost layers of the media. Flushing is an important process when contaminants are embedded within the media matrix. Using flushing methods can be a valuable tool in delivering chemicals to embedded contaminants or providing a mass of flowing fluid to actually move contaminants through the tortuous path in the media. So when considering cleaning, it is important to understand that all cleaning processes are not the same. Consideration must be given to the contaminant, location of the contaminant, and to the filter design. How do we test? To determine whether the filter has been properly cleaned or the internal pore structure is open and unplugged, testing is necessary. It is important to note that if the media is damaged or the pore structure is beginning to break down from possible corrosion or physical damage, filter performance and quality can be negatively impacted. The integrity tests used are bubble point and wetted airflow tests. The diagram shows the setup used for the bubble point and wetted airflow tests. The filters are wetted in a specific wetting agent and submerged to a defined depth. Air slowly fills the inside of the wetted filter while the pressure builds until the release of the first bubble is seen. Then the airflow rate is increased to provide airflow and bubbles across the entire filter. The bubble point is the pressure required to force the first stream of air through the largest pore or opening in the media. The bubble point pressure is inversely related to the pore size. Filters are bubble point tested to a specification that provides minimum bubble point criterion for the media. The wetted airflow test provides a measure of overall pore size and the condition within the media. In the WAF test, localized flow patterns across the media may indicate issues such as damaged or plugged media. For cleanliness testing, the dry air delta P or DAP test measures the pressure drop across the media when challenged with a set airflow rate. DAP values provide information on the degree of embedded contamination within the media matrix and can be used to determine the percent recovery of the media as compared to new. The picture shows a cross-sectional view of porous metal media matrix plugged with contaminants versus a view of cleaned or new porous metal media. Note the open pores in the picture of the clean media. The pores provide the channels through which the processed fluid flows. If contaminants plug the pores, then permeability decreases, along with porosity, if void spaces within the matrix become plugged. From these pictures, it is easy to see that if the pores remain plugged with improper or ineffective cleaning, frequent blowback and short filter life will result. As a result, testing is important. Carolina Filters develops solutions for difficult issues that impact filtration. Filtration issues can result in short filter life, increased frequency between blowdowns, and an increase in the clean DP. These problems can occur with variations in solid loading or characteristics from feedstock, such as bottom of the barrel processing. When the processing issues reach the point that the filters must be replaced, cleaning becomes a consideration for the filters being removed. However, it is important to understand that improperly cleaned filters may not resolve the refiner's issue. In the graphical representation of performance of a new filter versus clean filters, the gray curve describes performance of a new filter with expected time between blowback, resulting clean pressure drop, and on-stream life. The goal of cleaning is to return the filter media back to a like new condition. If the contaminant has been effectively removed, then the on-stream life and filter performance should approach that of a new filter. The blue and orange curves represent the performances of ineffectively cleaned filters, the blue curve, versus effectively cleaned filters, the orange curve. We will look at case studies that illustrate the blue and orange curves' performances. Carolina Filters was contacted concerning cleaning issues for units in delayed coking, FCC, and ADN applications. Issues were the same in all three facilities. As illustrated by the blue curve in the previous slide's graph, the cleaned filters exhibited a decreased filter life from 3 or more months down to several weeks, increased blowback frequency without a return to expected clean pressure drop, and higher than normal initial clean pressure drop. The test data gave no indication of issues with the filters, so plugged or damaged filters were reinstalled. On-stream performance continued to decay, and available filters were at a critical level. The issues also resulted in unplanned costs. New filters were purchased to support production at expedited charges. There were extra labor costs and production losses due to unplanned filter changeouts, along with extra cleaning charges due to more changeouts. By reviewing analytical data from media dissections provided by the manufacturer and users, it is evident that the filters were not being cleaned properly, which would be referenced by the blue curve on the previous graph. Analysis identified residual contaminants embedded within the media. Carolina Filters designed a deep cleaning process that chemically degraded, loosened, and removed the embedded contaminants. Also, test data was provided that defined the percent recovery for each filter and noted filters that had been returned to a like-new condition. Also, filters were recovered that were previously designated for disposal, which resulted in savings for the user. However, Carolina Filters did identify filters that could not be recovered, eliminating the installation and low porosity or damaged filters. Results of all three projects were the same. All three sites experienced improvements in on-stream life and performance. With all that has been discussed, the most important considerations are the benefits to the refiner, which are generally always related to cost and performance. Carolina Filters provides innovative solutions for difficult problems that affect performance, cost, output, and quality. The economics of properly cleaned filters reduces the need to purchase new filters, in which cleaning could be 50% or less of the price of a new filter. When performance issues create short filter life, turnaround associated with cleaning filters, which could be less than about 4 weeks, in comparison to the fabrication of new filters, which could be 16 or more weeks, could mean the difference between keeping lines running and shutting them down. However, the economics and turnaround benefits of cleaning filters versus new filters only applies if the filters are properly cleaned. Last but not least, cleaning is an environmentally responsible alternative to disposal. With disposal, there can be cost associated with contaminants and the disposal of metal filters. Carolina Filters uses a 3-part approach to cleaning. From the user, we ask for information on requirements, filter configuration and specifications, contaminants, and any other issues that may exist. The manufacturer provides knowledge of constraints due to metallurgy and configuration, cleaning restrictions, and integrity criteria. Carolina Filters uses knowledge of expert cleaning options for specific applications, metallurgies, and contaminants, along with testing for integrity and cleanliness. For the case studies discussed, analytical data from both the manufacturer and the refinery were invaluable in determining how to solve the issues. For over 50 years, Carolina Filters has been providing cleaning, testing, and other services to the filtration industry by attention to detail and quality service, innovative equipment and processes, and creative solutions to filtration issues.